Well, hello there. So let's talk about first order circuits. We're going to look at RC circuits where you have one capacitor and resistors, or RL circuits where you have one inductor and resistors. Those both give you first order differential equations. So we're going to look at those in the next few lectures. So we'll start off simple with some of the basics. So first, the new thing that we're going to have here, because we have differential equations with time, we have to talk about the time response. So transient response is a term that you'll hear a lot, and it's when you've changed something and how it comes back to steady state. So it's the initial reaction when you have a sudden change. So switches in general are used to create a transient response. When you close a switch, it changes the circuit, and we look at initially where it is, and eventually there's usually an asymptote, sometimes some other kind of steady state response, but usually a steady DC for these cases. There are a number of different functions of time that are useful when we're talking about the math behind first order differential equations. We don't go into them into a lot of detail, but the book has more information. So things like the step function u of t, the ramp function r, the pulse rect, and we do have a fair amount of exponentials because of the solutions to first order differential equations. So e to the negative t over tau is something we'll talk about quite a bit. So just looking into these exponentials a little bit more, one really important parameter is the time constant tau. So with first order systems, you have generally one important parameter, second order generally two, and so forth. So the time constant is one way to think about how a first order system works. And it's how long it takes for something to decay. So here we have decay versus time with different exponents, different time constants up here. So the time constant is the denominator of this equation. So this has a time constant of 2 seconds. This has a time constant of 1 second. So shorter time constant means things happen faster. Longer time constant is slower. Time constant units are seconds because what goes in the exponent can't have units, so seconds divided by seconds gives us no units. In one time constant, the time goes from 0 to tau seconds, and between 0 and tau seconds, that's one time constant. On the x-axis, the voltage in this decay drops by e to the negative tau over tau. So e to the negative 1 comes into our equation. So that's 0.3679 times the initial amplitude. So we're at 36.79% of our starting point at one time constant in. This function here with 1 minus the exponential times an amplitude that is our asymptote is a little bit more common, and this u of t means it's the step function, is step function which is 1 for t greater than 0 and 0 otherwise, so we get this flat spot here. But this is the time constant again, and so in one time constant tau seconds, we go from 0 up to 63.2% of our final steady state value. So, and that's, it seems mysterious where the 63% comes in, but it's just e to the negative 1. 1 minus e to the negative 1 is 0.6321. A little terminology here for our response. Usually it's broken into two parts, and you'll see this in your differential equations class. We have the natural response, which is what happens when nothing's forcing it. So if you think of things like pendulums, if you just let it go, it swings back and forth. That's its natural response. The forced response is something driving it. So if somebody's pumping their legs on the swing, you can get a forced response that's different from the natural response. And the complete response is both of them. You can also hear these divided up in terms of the time dependence. So the transient response is what happens in the initial beginning of the response, and then that goes away and you're left with the steady state response. And often the natural response decays, so it's mostly the transient response. And the steady state is what happens if you wait a little while. Sometimes we flip a switch. We don't care what happens right away. We want to know what happens in the end. And so that's when the steady state response is useful. And then, of course, you add them together, superposition, to get the total response. Sometimes in your differential equations class, you might hear the particular solution and the homogeneous solution. A homogeneous solution is generally the natural response. Particular solution is the forced response. So you might hear those words as well. Okay, so finally into some circuits. This is kind of a special case because this is just the natural response. There's no forcing function. So it's a good start, but the next one where we do the total response, that's the one you're going to want to keep handy because it includes this case as well as the more general case. Okay, so let's take a look at this. We've got a circuit with a capacitor, one capacitor, and sources and resistors. And there's a switch. So this switch has position 1 and position 2, and then in the drawing it looks like at t equals 0 we go from 1 to 2. So switches give us our initial conditions. That's the way I think of them normally. And so we have two circuits depending on where the switch is. So for t equals 0 minus, just before the switch is thrown at 0 seconds, we've got this one, and generally it will say something like it's been in this position for a long time. That means it's in steady state. In steady state, the capacitor acts like an open circuit. So here is what our circuit would look like after a long time in the initial position. And so we can use this without any differential equations to find the voltage across the capacitor just before the switch was thrown. That's our initial voltage. And from this you can see that V equals Vs. Because there's no current flowing here, there's no voltage drop across the resistors. So this gives us our initial condition. Because the voltage across the capacitor cannot change instantaneously, which we talked about in the previous lecture, most people just forget about this, but it is important to realize that this is a justification for the fact that at t equals 0, before we throw the switch and after we throw the switch, that voltage has to be the same, because the current won't be the same, but the voltage is. So we know that the initial voltage on the capacitor is Vs. Then for t greater than 0, the switch goes down here, and then we just have the capacitor and the resistor and no source. That's why it's the natural response. So we can use our regular analysis techniques here. So we can do Kirchhoff's voltage law around the loop, and IR is the voltage across the resistor, and V is the voltage across the capacitor. So we can add those together and they must sum to 0. So this is Kirchhoff's voltage law here. Now we can use the definition of the IV relationship for a capacitor. I is C dV dt, and get rid of I in this Ohm's law equation. And we come up with R times C dV dt plus V equals 0. And this is a nice first order differential equation, homogeneous differential equation because it equals 0. That's the natural response. So if we divide by RC on both sides, we get this kind of the standard. What we're looking for here is a cookbook solution to these equations so that we don't have to do differential equations every time. We can draw a circuit in a standard way, which gives us a standard equation and a standard solution. We're not quite there. So here is the solution to our standard differential equation. So I won't go through it in a lot of detail. The book does a nice job at this too, but we multiply both sides by e to the at. It's kind of a trick. And then if you factor things out carefully, we can work it out that the derivative of v e to the at, this is the product rule, and that looks like our differential equation. So we get this, keep going. And what we find is this exponential form. So the voltage as a function of time is the initial voltage times e to the negative t over tau, where tau is RC. So that's pretty useful. But this is just the natural response. So if we look at that, it's starting at the source voltage Vs, and we get this exponential decay. This is the voltage versus time plot. If we do current, it's C dV dt. So we get a minus sign in there because of the negative t over tau. So this is current versus time, and you could do power and energy as well from the general equations for those. But they're all some form of decay. Okay, so this is the useful one, the one that you'll use the most. And it follows basically the same procedure, which is why we started with the simpler one. So here we've got a single capacitor and then a complicated circuit with lots of resistors, sources, and everything but just one capacitor. And here we have a switch. So the switch is at 1, and then at t equals 0, it's switched to 2, and now 2 has a source involved. So again, before the switch was thrown, it was in that position for a long time, in position 1 for a long time, so we're in steady state. So again, no current here because this is an open circuit, and the voltage across the capacitor is Vs1. So this could be a more complicated circuit, but you do your basic analysis, node analysis, and find the voltage across the terminals where the capacitor would go. That's your initial conditions. Then we look at the circuit with the switch moved, the t greater than 0 position. So this one down here, we put the switch down there, and we've got a voltage source and a resistor and our capacitor. It's important to notice this general thing is a Thevenin circuit, so it represents so many more complicated circuits because we can always make a Thevenin. So for t greater than 0, we have this circuit, and if we do Kirchhoff's voltage law, it's the same as we just looked at, but now we have the Vs2. So minus Vs2 plus IR plus V equals 0. Do the same trick, I is C dV dt, to replace the I and divide things around, and we get this is our standard cookbook equation. First order differential equation with a 1 here on the derivative, A and B then are constants. So A is 1 over RC, and B is Vs, the source voltage, divided by RC. This is the solution, and we just looked at solving it with 0 instead of B. So this is the more general one. If you want to solve that particular case, you can set B to 0 and get the right answer. It's a very similar process where we use this e to the at trick. And what we end up with is here. We'll just skip to the end. So voltage as a function of time across the capacitor has two constants, V infinity, the steady state voltage at the end of time when t goes to infinity, and the voltage initially when the switch was thrown. That constant comes up at two places, e to the negative t over tau. And again, tau is going to be our RC from our circuit. So the process to find the solution, once we know this equation, is we need V infinity, we need V0, and we need tau. There's a more general case if the switch is thrown at t0 instead of 0, and it just gives us a little bit of an offset, t minus t0 here. And then the initial condition, of course, is when the switch was thrown. Okay, well that's the general beginning. What we're going to look at next is the specific steps. We're looking at a very limited set of problems here, so I'll show you step by step how to do an RC circuit, complicated circuit with one capacitor. We'll also do RL coming up in the next videos. So thanks for sticking with me through the theory. We'll see the examples next.